Hello everyone. Welcome back to class. Let's begin with a tiny spark of curiosity. Tell me, have you ever used a magnifying glass to focus sunlight on a piece of paper? Of course you have, or at least you've tried. And within seconds, that poor paper starts smoking and burning. Don't worry, I won't ask who tried it on their homework. That, my friends, is not magic, it's pure science, and it's the power of a lens at work. Now, what exactly is a lens? Think of it as a special piece of glass or plastic that's perfectly shaped, not flat, but curved, like a little slice of a ski air. And here's the clever part, this curved surface makes the lens bend light in very particular ways. Some lenses are like traffic police, they gather wandering light rays and direct them all to meet at one single point. These are called converging lenses. Others are more like mischievous friends at a party. They scatter the light rays apart so that they never meet. Those are diverging lenses. You see, this simple bending trick is what allows us to read tiny letters with spectacles, zoom in with a camera, or even make giant telescopes that peer into the farthest galaxies. By the end of this session, you'll not only know what lenses do, but also why they behave the way they do. And trust me, once you understand that, you'll start spotting lenses everywhere, from the lab table to your own eyes. Alright class, now let's meet the two big families of lenses, convex and concave. Think of them like cousins in the same family, but with completely opposite personalities. First, the convex lens. Picture it as two balls stuck back to back, bulging outward in the middle. Now here's the fun part. When parallel rays of light enter a convex lens, the lens bends them inward until they all meet at one point. That special meeting spot is called the focus. Because it gathers or converges the light, we proudly call it a converging lens. You might remember this from the magnifying glass experiment, burning a paper under the sun. Yup, that's a convex lens flexing its muscles. Now comes the concave lens, the shy cousin. Its surface curves inward, almost like the inside of a cave. And true to its shape, instead of bringing rays together, it pushes them apart, spreading them outward. But here's the trick, if you trace those rays backward, they look as if they all started from a single point behind the lens. That's why we call it a diverging lens. It's like someone giving directions but sending everyone to different corners of the room. And of course, these aren't just fancy glass toys. Convex lenses are the heroes inside microscopes and cameras, helping us see things bigger and clearer. Meanwhile, concave lenses play doctor. They sit in spectacles to fix short-sightedness so that distant objects don't stay fuzzy forever. Imagine watching your favorite cricket match on TV without them. Players would look like colorful blurs running around the field. So remember, convex gathers light like a boss, concave scatters it like a prankster, and both are equally important in our daily lives. Alright students, time to get friendly with some important lens vocabulary. Think of this as learning the nicknames of your new classmates before you start working on a project together. First, the principal axis. Picture a perfectly straight line that passes through the centers of both spherical surfaces of the lens. It's like the main reference line. Everything else in the lens's story is measured with respect to it. Next, the optical center, often shown as the point O. This is the special VIP point inside the lens. Any ray of light passing through it doesn't bend at all, it just goes straight, as if the lens politely steps aside and says, "Go right ahead, no questions asked." Now, the principal focus, marked as F for a convex lens, rays coming in parallel to the principal axis bend and actually meet at this point. For a concave lens, the rays spread out, but if you trace them backward, they appear to come from this point. So in short, convex gathers them together, concave makes them look as if they started from behind the lens. Finally, the focal length, written as f. This is the distance between the optical center and the focus. And here's the cool part. The shorter the focal length, the more strongly the lens bends light. A lens with a short focal length is like a strict teacher. It doesn't let light rays go straight, it bends them sharply. That's why magnifying glasses with short focal lengths can make even a tiny ant look like a giant monster in your notebook. Alright class, here come the 3 golden rules of ray diagrams, the holy formula for lens problems. If you remember these, drawing ray diagrams becomes as easy as doodling in your notebook. Well, almost. Rule 1. A ray parallel to the principal axis. For a convex lens, this obedient ray bends and passes through the principal focus. For a concave lens, it's a rebel, it spreads out. But when you trace it backward, it seems to come right out of the focus. Think of it like water pipes. One pipe directs flow neatly to a single tank, convex. The other splashes water everywhere, but you can guess where it would have come from, concave. Rule 2. A ray passing through the optical center O. This one is special. It doesn't bend, twist, or scatter. It just marches straight through, undeviated. I like to call it the lens's secret expressway. Imagine you're stuck in traffic, but one student has a VIP lane that goes straight through without stopping. Lucky them. That's exactly what this ray enjoys. Rule 3. A ray passing through the focus before hitting the lens will come out parallel to the principal axis on the other side. So if the previous rule was parallel goes to focus, this one is the reverse, focus goes to parallel. Nice and symmetrical, right? Like the give and take policy of physics. And here's the magic, you don't even need all 3 at once. Just pick any 2 rays following these rules, draw them carefully, and wherever they meet, or appear to meet, that's your image location. It's like a treasure hunt, 2 clues are enough to find the hidden spot. Okay class, now it's time for the most important relation in lens physics, the lens formula. This is the golden equation that links the object, the image, and the lens itself. Ready? Here it comes, 1 divided by f is equal to 1 divided by v minus 1 divided by u. Here, f stands for the focal length of the lens, v is the distance of the image from the lens, and u is the distance of the object from the lens. Think of it like a friendship triangle, object, image, and lens are all tied together by this single relation. Forget one, and the others complain. Distances measured in the direction of the incident light are taken as positive. In other words, if the light is moving forward, so are the positive values. Distances measured opposite to the incident light are negative. So if you're going against the traffic, be prepared for minus signs. And finally, heights, anything measured above the principal axis is positive, while anything below the axis is negative. You can think of this like classroom seating. Students sitting in the front row, in the direction of the teacher's gaze, are positive, the ones sneaking to the back row are negative, and those sitting above or below the bench line also get their own signs. So to sum it up, the lens formula is our best friend in locating images, but it only works smoothly if we respect the sign convention. No cheating, no shortcuts, because in physics, the signs matter just as much as the numbers. Alright students, time for a numerical adventure with our convex lens. Let's break it step by step so it feels more like solving a puzzle than a scary math problem. Step 1. Given values, we are told the object is placed 20 centimeters in front of a convex lens. Using our sign convention, the object distance u is minus 20 centimeters since it's in front of the lens. The focal length f is plus 15 centimeters because it's convex and we treat convex lenses positively like optimistic friends. Step to the lens formula. Here comes our trusted relation. 1 by f is the same as 1 by v minus 1 by u. This is the backbone of lens calculations. Time for a little fraction workout. Combine them with denominator 60. 4 by 60 plus 3 by 60 makes 7 by 60. So 1 by v is 7 by 60. Flip it and we get v as 60 by 7, which comes to about 8.57 centimeters. That's where the image forms on the other side of the lens. Step 5. Nature of the image. Now let's interpret. Since we turn out positive, the image is real. Real images form on the opposite side of the lens, and in ray diagrams, they come out inverted. And because the image distance is less than the object distance, the image will also be smaller in size. So we conclude real, inverted, and diminished. Think of it like this. You place a candle in front of a magnifying glass, and on the other side, you see its sharp little image on the wall, flipped upside down and tinier. That's exactly what we just calculated. And there you go, step by step. No panic, no shortcuts. Just careful use of the formula, the signs, and a bit of fraction practice. All right, class, let's take a quick recap of everything we've learned about lenses. Think of this as packing up your school bag neatly before heading home. We are just putting all the key ideas in the right slots. First, what is a lens? It's simply a transparent medium, usually glass or plastic, bounded by two spherical surfaces. Its superpower is that it bends or refracts light. Not magic, just physics at work. Now, the two families, convex and concave. Convex lenses gather or converge rays of light, like a team captain pulling players together. Concave lenses do the opposite. They spread or diverge rays, like friends running in all directions at recess time. Then we had our key terms, the principal axis, the optical center, the focus, and the focal length. These are the ABCs of lens language. Without them, ray diagrams would feel like reading a book without knowing the alphabet. Next comes image formation. We used ray diagrams and the lens formula. 1 by f is the same as 1 by v minus 1 by u. This simple-looking relation is our best tool for solving numerical problems about where images will form and what their nature will be, real, virtual, magnified, or diminished. And finally, why does all this matter? Because lenses are everywhere. From the spectacles that help people see clearly, to cameras capturing your best selfies, to microscopes that zoom into cells, and telescopes that zoom out to galaxies. Wherever there's a need to bend light smartly, lenses step in. So remember, lenses are not just classroom diagrams, they are the hidden heroes of optics, quietly shaping how we see the world.